Hello everyone and welcome to the channel. Fusion is being sold as the moment humanity finally escapes the energy trap, limitless clean power, no CO2, no fuel wars. But if you look at the numbers, the uncomfortable detail is simple. The bright future is being paid for right now by people who will never see it on their electricity bill. And this is where the official story starts to fall apart. We are told that fusion is about clean energy for everyone. In practice, it is a dense knot of capital expenditure, regulatory engineering, geopolitical positioning, and very long payback horizons, wrapped in the language of hope. The physics is real, the timelines are political. Now, here's the part that keeps economists awake at night. The IAEA counts more than 160 fusion devices worldwide. Almost 40 countries already have dedicated fusion programs, and private investment has passed $10 billion. That's a serious stack of chips on a technology that still hasn't produced a single commercial kilowatt hour. This is the structural flaw you can't fix with a press release. The story is about limitless energy, but the system underneath is about who owns the reactors, who writes the regulation, and who absorbs the risks in the next 30-50 years. Fusion, in simple terms, is the attempt to do what the sun does inside an expensive metal donut down the road from your city. You heat plasma to insane temperatures, hold it in place with magnetic fields, and try to extract useful power without melting the hardware. On paper, it's elegant. In engineering terms, it's like docking a tanker in a hurricane, blindfolded. Right now, the flagship of this world is ITER, the International Thermonuclear Experimental Reactor. Russia was one of the initiators and remains a key contributor. Around ITER, you have a whole zoo of other machines: the Japanese European JT60 SA, the Chinese EAST, the American Spark and INF, the German Stellarator, W7X, and a series of Russian tokamaks like T15MD, T11M, and the spherical Globus M2. Each of them is a different way of answering one question: can we hold hot plasma long enough and stable enough to make the whole thing pay? In short, the math doesn't care about our ambitions. Either the device produces net energy at a cost the grid can tolerate, or it becomes a very expensive monument to optimism. There is one more layer. Fusion is no longer just a physics curiosity, it is being written directly into national energy strategies. Governments are not treating it as a science project, but as a future pillar of industrial policy, foreign policy and security. Almost 40 countries already have dedicated fusion programs or regulatory frameworks in development. Energy companies are signing memorandums of understanding with fusion developers. Industrial players in automotive, aerospace, and digital sectors are quietly reserving a place for fusion in their long-term portfolios. Officially, this is framed as innovation. In practice, it behaves like long-dated optionality, a bet that if fusion works, you want to be a technology owner, not just a customer. So what does this look like at the level of physics and money? On the physics side, the big trend is obvious: high-temperature superconducting magnets. HTS magnets allow stronger magnetic fields and therefore more compact fusion devices. Smaller devices mean less steel, less concrete, and in theory faster development cycles and lower capital costs per kilowatt. That's why you see a rush into compact tokamak designs using HTS coils. But stronger fields also mean higher mechanical stresses in the magnet systems, tighter engineering margins, and much more brutal heat loads on the plasma-facing components. In short, every gain in compactness is bought with new headaches in material science and engineering. At the same time, traditional large devices are still essential. ITER remains the reference laboratory for burning plasma physics. National programs like Russia's projected TRT tokamak, a tokamak with reactor technologies, are designed to bridge between pure experiments and something closer to a prototype power plant. TRT is supposed to test advanced materials, validate reactor-level components, and plug into international collaborations. If it works, it becomes a national anchor for fusion research and, more importantly, a training ground for entire supply chains. Now, here is where the story stops making sense for an ordinary viewer. None of this is cheap and none of it runs on fairy dust. Let's talk about costs. In the IAEA review, they cite a study from IT's Energy Initiative on the role of fusion energy in a decarbonized electricity system. To avoid fantasy, they do something very sober. They don't pretend to know the exact cost of future fusion plants. Instead, they model scenarios based on capital cost per kilowatt of installed capacity, and then they run the numbers against a decarbonized grid. In the baseline scenario, they assume $8,000 per kilowatt of fusion capacity. At that price, fusion starts as almost nothing. Roughly 2 terawatt-hours of generation in 2035, which is statistical noise on a global scale. By 2050, that grows to around 375 TWh. By 2100, if the learning curve holds, fusion generation could reach 25,000 TWh. That would be about 15% of world electricity by 2075 and 27% by 2100. So let's take a breath. Where does this leave us so far? We are being sold a narrative of limitless energy just around the corner, but even in the optimistic modeling, fusion only becomes a major player in the second half of this century. If you are paying high energy bills in Germany, Lithuania, or Italy today, this is not a rescue plan. This is a long-term structural hedge for the system. And this brings us to the one number that changes the entire equation. The same modeling shows that compared with a decarbonization scenario without fusion, global GDP by 2100 rises by about 0.4% in the baseline cost case, and 0.9% if fusion capital costs fall to around $5,600 per kilowatt. This number is the quiet part, said out loud. For the global macro system, that's a non-trivial benefit. For an individual household, it's almost invisible. In short, fusion looks less like a revolution for your wallet and more like a gentle tilt in the long-term trajectory of the world's balance sheet. Now, let's look at the players and their incentives. First, states. For Russia, fusion is about technological sovereignty, continuity of high-end nuclear expertise, and future export potential. National programs like the New Atomic and Energy Technologies Project and the Federal Initiative on Fusion Technologies are framed as part of a broader push to stay in the top league of complex energy systems. The new Federal Law 342 FC extends atomic energy regulation to fusion devices, creating legal ground for future fusion plants, including those with nuclear materials. It takes effect in 2027. On paper, that's boring legalese. In practice, it's a signal the state is preparing for fusion not only in laboratories but as part of the regulated power system. For the EU, fusion is folded into the trinity of decarbonization, strategic autonomy, and industrial policy. Being tightly tied to projects like ITER and European Japanese machines such as JT60SA, Brussels gets to say we are not just taxing carbon, we are building the next generation of clean baseload. For politicians, fusion is perfect, it is green, it is high-tech, and it matures far beyond the next election cycle. For the US, fusion plays into private-public partnerships and technological dominance. Devices like Spark and the NIF experiments form part of a broader ecosystem where venture capital, defense contracts, and federal research funding blur into each other. The US position is simple. If fusion pays off, it should be on American hardware, with American intellectual property at the core. China and other Asian players see fusion as one more field to avoid technological dependency and to secure long-horizon options in a world where fossil fuel logistics and maritime choke points are becoming more politicized. If you're watching this from Germany or the Baltics, ask yourself, does this look like a coordinated humanitarian project or a structured race for future market share? The public rhetoric is about global cooperation and energy for humanity. The private briefings are about supply chains, licensing, component exports, and grid-scale assets that will operate for 60 years. This is the structural flaw you can't fix with a nice speech at the climate summit. Second, regulators. Regulatory frameworks for fusion are now being written in real time. The IAEA notes that there is still no globally agreed definition of a fusion power plant, but many countries are already extending their nuclear laws or drafting new rules to cover fusion devices that produce electricity or heat. Some regulators start with research machines, use them as a sandbox, and then extrapolate to power plants with some modifications. In short, the law is chasing the hardware, and both are chasing political narratives. From a system point of view, regulation has two main jobs here. One is obvious, safety. We're still dealing with high energies, complex materials, and in many designs, some amount of radioactive inventory. The second job is less visible, defining who is responsible when things go wrong and who gets paid and how when things go right. Capacity payments, grid access rules, liability frameworks, all of this will shape whether fusion ends up as a natural monopoly, a club of a few state corporate giants, or a more open ecosystem. This is the part no politician wants to explain on TV. It's one thing to say cheap, clean fusion for everyone. It's another to say, by the way, it will be owned by the usual suspects financed by public money, and your role is to pay the bills for decades before it stabilizes prices. Third, technology and industry. High-temperature superconductors are moving from specialist jargon to the core of fusion roadmaps. HTS magnets promise stronger fields and more compact tokamaks. That means potentially lower capital costs, shorter construction timelines, and a faster learning curve. At the same time, they introduce mechanical stress problems, cooling challenges, and brutal heat fluxes on internal surfaces. So what do we get in practice? We get an ecosystem where state labs, private startups, and traditional nuclear vendors are forced into uneasy alliances. Big engineering companies see fusion as a future order book. Component suppliers for vacuum systems, cryogenics, high-power RF and plasma diagnostics quietly position themselves for long-term contracts. Now, here's the part that keeps system planners awake at night. Fusion doesn't arrive in a vacuum. It has to integrate into grids, already struggling with variable renewables, aging nuclear fleets, legacy gas infrastructure, and political promises to phase out coal. Fusion, if it arrives, will slot into a network that is already structurally stressed. In short, fusion is less a new world and more a new heavy module bolted onto an already creaking machine. So what does all of this mean for ordinary people? First, fusion is already on your bill, even if you never see the word. Public research funding, tax credits, infrastructure grants, international contributions, all of this is financed by taxes and public debt. When your government sends money to ITER or a national fusion program, it doesn't come from an abstract space. It comes from the same fiscal bucket that could have funded insulation programs, grid modernization, or lower VAT on electricity. This is the moment a fusion strategy becomes a quiet line item in your household budget. Second, fusion timelines do not match household timelines. If you are 40 or 50 today in Europe, the optimistic scenario is that fusion combined with other technologies helps stabilize your children's energy costs by the time they are middle-aged and reduces the long-term upward pressure on taxes needed for climate policy. That's valuable at a civilizational scale, but it's a bad answer to the question, why is my energy bill so high this winter? Third, fusions promise GDP gains plus 0.4% or 0.9% by 2100 compared to a fusion-free decarbonization path are macro-level smoothing. If you work in manufacturing or energy, you've seen this movie before. Sector-level shifts can be brutal even when the overall GDP line looks neat. If fusion ends up owned by a small circle of players, it may support state budgets and corporate earnings, while the distributional effects for the middle class remain ambiguous. You see the problem here, right? A technology that is framed as for everyone may, under current institutional setups, end up reinforcing existing concentration patterns in energy and finance. Now, does that mean fusion is a scam? No. The physics is legitimate, the research is serious, and the potential system-level benefits are real. A high-density, low-carbon, controllable power source with minimal fuel logistics is a strategic asset in any scenario of fragmented global trade, unstable maritime routes, or resource conflicts. For countries like Russia, the US, China, or large EU economies, owning fusion competence is a way to reduce vulnerability in a world where shipping lanes, pipeline routes, and rare earth supply chains are all weaponized. If you take one thing from this video, let it be this: fusion is not about miracles, it is about optionality. Optionality at the scale of continents, bought at the expense of taxpayers who will mostly experience it as higher costs now and slightly less chaos for their grandchildren. There is one number in this story that nobody in Brussels likes to say out loud: the time horizon. All the serious scenarios treat fusion as a significant contributor only after 2050 and often closer to the end of the century. Politically, this is almost unusable. Economically, it's tolerable because markets and states can price long-dated options. Socially, it is a problem because electorates live in 4 or 5-year cycles. So where does that leave us? It leaves us in a world where fusion is both oversold and understood. Oversold, because the public narrative treats it as a near-term solution to today's energy and climate pressures. Understood, because in the technical and economic literature it is treated for what it is: a high-risk, high-reward long game that might slightly tilt the trajectory of global energy costs, emissions, and GDP, if we get the physics, engineering, regulation, and financing all roughly right. From my corner of Europe, inside the EU but outside the core capitals, the picture is simple. Countries like Lithuania, Latvia, Estonia, Portugal, or Greece are unlikely to host the flagship fusion plants or dominate the IP stack. Most will participate as contributors, test sites, or in the end just customers paying a regulated tariff for energy produced in someone else's machine. The strategic gain is indirect: a bit more stability in regional grids, a bit less exposure to imported fossil fuels, and maybe slightly less aggressive climate taxation if fusion takes some pressure off other measures. Thank you for watching. Take care of yourselves and your loved ones, and try to remember, slogans don't power grids, systems do.